This is going to be the first of three topics that focuses on either counting techniques or problems that require counting techniques in order to in order to solve them. We're going to be focused on the sum and product rules in this video. So the sum rule is really simple. It says, hey, suppose you have two tasks that you need to accomplish, two tasks that can't be done at the same time. If the first task can be done n sub 1 ways, and the second task can be done n sub 2 ways, then the two tasks can be performed n1 plus n sub 2 ways. There's going to be n sub 1 plus n sub 2 ways to do it. And the key is that you can't be able to do the two things simultaneously. So in this first example, we've got 5 pairs of shoes, 3 pairs of sandals, 6 pairs of boots, and the question is, in how many ways can you select today's footwear? And the idea here is we can't have tennis shoes, sandals, and boots worn simultaneously. So if we're selecting today's footwear, there's going to be 5 plus 3 plus 6 ways to do it, or 14 ways to select something to wear today. The second example, you've got a senior project that needs to be done, and there are 12 calculus-based projects, or 8 calculus-based projects, 12 discrete math projects that you can choose from, and there's 4 non-Euclidean geometry topics that you can choose from. So the idea is that you're not going to do more than one senior project, which means you can't work on 2 of these projects simultaneously. So because there's only one senior project that can be done, we're just going to add up, hey, there's 12 plus 8 plus 4 possible senior projects that you could work on, or topic areas that you could have. So 24 possible senior projects. The product rule. With the product rule, what you have is a procedure that's going to be done that can be composed into 2 tasks or more. This generalizes to an arbitrary number of tasks. And the idea is if there's n1 ways to do the first task, and there's n sub 2 ways to do the second task, then there's going to be n sub 1 times n sub 2 ways to do the entire procedure. So for example, if you have 5 different colors of socks and 6 different pairs of shoes, it says in how many ways can you select a shoe-sock combination. So you're going to pick the sock that you're going to wear, and the procedure, step 2, is going to be once you've selected and put on your sock, you select and put on your pair of shoes. So we're going to say there's 5 times 6 is 30 ways to wear your shoe-sock combinations. The idea is this is really, we're working with natural numbers, and we're working with repeated addition. So the idea is you pick your sock. So use a letter to represent sock. Let's say we use S to represent sock. There's going to be the first sock you can pick, the second sock you can pick, all the way down through your 5th sock. And for each of these 5 choices, they're going to be paired up with 6 choices of shoes, right? So I guess I can't use S for shoe. So foot covering. So you have foot covering 1, foot covering 2, sock 1 can be paired with either of those all the way through, hey, there's 6 possible foot coverings that are types of shoes. And there's going to be 6 of these, and these 6 are going to pair up with each of our 5 sock choices. So you wind up with 5 times 6 is 30 possible ways of combining these things. The second example, we have chairs in an auditorium that we're going to label with a letter and a positive integer that can't exceed 100. And it says, what is the largest number of chairs that can be labeled differently? So the idea is that you're doing a 2-step procedure. You're first choosing a letter. You're then choosing a positive integer, right? So for example, we could label a chair A26. So this is a 2-step procedure, and then you ask the question, how many ways can you accomplish the first task that leads to completion of the procedure? And the first task is to select a letter. So if we assume we're working with the English alphabet, there's going to be 26 choices. And each of those 26 choices can be paired up with some number of integers. So we would need positive integers. So that means starting at 1. And then not exceeding 100 means we get to include 100. So there's going to be 100 integer choices. So we get 26 times 100 is 2600 ways to label chairs using a letter followed by a positive integer between 1 and 100. So next example, we have how many functions are there from a set with m elements to a set with n elements. So here we want to remember that a function is just a mapping. So for example, I could have a set of 3 elements, and I could have a set of n elements. Maybe I have an A and a B and a C. And remember, to be a function, we have inputs that map to outputs, and there's different ways that we're allowed to map them. We can map 1 to A, we could map 2 to A, we could map 3 to A would be one way to do this. And this would be a function because each input maps to exactly one output. So the only way we would violate the definition of function would be if we had one of these elements mapping to 2 elements. So if I map 1 to A and 1 to C, I'm not a function because I have an input mapping to 2 distinct outputs. So I'm allowed to map every input to the same output. I'm allowed to map some inputs to the same output, and maybe I can map the 3 over to the C. I can choose to map each input to a unique output. And I could create in a one-to-one function, for example. So the idea is, as long as we don't map inputs to more than one output, we have a function. So step 1 is, for creating our function, is select one of the m elements, and then we map each of the m elements over to n elements. So there's going to be m times n ways to create a function. Each element maps to n possible choices for elements in the output set. Now the second part here says, hey, suppose that we put the stipulation on that we're going to make a one-to-one function. And remember, with a one-to-one function, if we have inputs and we have possible outputs A, B, C, with a one-to-one function, once you map an input to an output, you cannot map another input to that output. So a one-to-one function has the stipulation that each output in your output set must have only one pre-image in the input set. So once I map 1 to C, C is no longer a choice. I can then take 2 and I can choose to either map it to A or B. So notice I only have 2 choices now. I have 1 fewer choice than I did before. And now that I've mapped 1 to C and 2 to A, 3 to make a one-to-one function can only map to B. So I had only 1 choice. So what we want to notice here is that to make a one-to-one function, our choices are decreased, the number of choices we have decrease by 1 each time we map an input element to a unique output element. So if we're going to work this out, we're working with a set of m elements and mapping it to a set of n elements. We are going to map each of the m elements. So I'm going to map m elements, and I'm going to map them to my set of n elements. So for my first element, when I map it, I need to realize that I have n choices. I can map it to any one of the n elements that are available. Then for my second choice, I can't choose whatever I chose before, so I'm going to have 1 fewer elements to choose from. And when I come to map my third element in the set of m elements, I'm going to have one fewer choice than I did the previous time. And this is going to walk all the way down to where in the last step there's only going to be one possible choice. So I get n times n minus 1 times n minus 2 all the way down through times 3 times 2 times 1. And we want to recognize that this is just the factorial function. We're going to have n factorial choices if the set M has the same cardinality as the set N. In other words, if the two sets are the same size, we would run out. If the two sets aren't the same size, then we might not run out of elements. So let's say I'm mapping to a set that is larger than the set M, so that there are more elements in the set with n elements. In other words, things will look a little different. If n is greater than m, we're not going to run out of elements. So when we map our m elements, there's m elements sitting here. Well, the first element in the input set, there's going to be n choices. Then there's going to be n minus 1 choices. And then there's going to be n minus 2 choices. And then I need to decide what to put here. So the question is it n minus m choices? If we've mapped m of the items. So for example, if I have a set that contains, let's say, 3 elements and a set that contains 6 elements, when I map my first element here, I'll be down to 2 elements left to map, and I'll have 5 to map to. And when after I map the second one, I'll be down to 1, and I will have 4 to choose from. And then I will map all 3, and then how many choices do I have here? I have 4 choices. So if I do 6 minus 3, that gives me 3, which is not quite enough. So what you see is that I have to get the number of elements I'm choosing to map to. I have to add 1 to that 3. I have to go 3 plus 1. So we need to make an adjustment to this and say, hey, there's going to be n minus m plus 1 elements to choose from. So we get the product n times n minus 1 times n minus 2 times n minus m plus 1. And the question is there a compact way to get this? And there is, because we could put n factorial, which would give us everything, right? This would be n minus m would be next, times n minus m minus 1 times all the way down to times 3 times 2 times 1. If we put n factorial, we get the entire factorial, but we want to clean out this stuff. So if we divide by n minus m factorial, that's horrible. If we divide by n minus m factorial on the in the bottom, that would cancel out this extra stuff and leave us with exactly what we need. Product rule. So more product rule examples. The format of telephone numbers in North America is specified by a number plan. Telephone numbers consist of 10 digits. And those 10 digits are split into a 3-digit area code. So when you're selecting numbers, you get to select your 3-digit area code. This is the area code. And then there's a 3-digit office code. This is the office code part. And then we've got a 4-digit station code, 1, 2, 3, 4. And so we're told here we're going to represent possible choices by x. If we have an x, that means we can choose digits 0 through 9. We're going to let n represent anything where there are numbers 2 through 9. And then we're going to let y over here denote a situation where we're only allowed to choose a 0 or a 1. And then we're identifying that in the 60s and earlier, phone numbers had the form N, Y, N, 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 X, 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 and after 1960, the format has changed to an NXX form, NXX, XXXX. And so an X represents our ability to choose numbers 0 through 9, and what we want to recognize then, if we're choosing numbers 0 through 9, that means we have 10 choices. N represents the ability to choose numbers 2 through 9, and if we're choosing numbers 2 through 9, there are 8 possible choices. And Y, if we can only choose the number 0 and 1, that means Y represents a case where we have only 2 choices. So prior to 1960, this is the format that numbers had. So at each step in the process, you say, hey, the step 1 is choose a number, but I only have, because it's an N format, I only have 8 choices. Now I can choose a number for my second slot, which means I have 2 choices, and it's an NYN, so 2 choices in my second slot, times 8, times, now I'm going to fill in the next slot, times 8, times 8, times X represents 10, times 10, times 10, times 10. And then we can combine things with exponents, so we're going to have 8 to the 4th times 10 to the 4th times 2 possible phone numbers. And then the format changed. That changes your choices. N means you have 8 choices, times X means we have 10, times 10, times 8, times 10, times 10, times 4 more 10s, which means we have 8 squared times 10 to the 2, 4, 8, and times 10 to the 8th possible numbers. So we can get things a little bit more complicated now. We can say, well, what if we need to do product rule and the sum rule at the same time? So here we have an example. Consider a computer network on which each user is assigned a password. Each password must be 6, 7, or 8 characters long. And what we want to recognize is that an individual can't have simultaneously a 6, 7, or 8 character long password. You can only have one of the 3. So that's where the sum rule is going to come into play. And it says each character must be either an uppercase letter or a digit. And furthermore, each password must contain at least 1 digit. How many possible passwords can we make? So I want to consider the case where I make a 1, 2, 3, 4, 5, 6-digit password. I want to count the number of ways there are to make a 6-digit password, and I'm going to use the sum rule to say, hey, how many ways can I make a 1, 2, 3, 4, 5, 6, 7-digit password plus how many ways are there to make a 1, 2, 3, 4, 5, 6, 7, 8 character long password. And then we need to take into account the fact that we have to have at least 1 digit, and we'll adjust for that at the end. So the number of ways you can make a 6-digit password, well, we need to think about what are our choices. We can use uppercase letters. So if we assume English alphabet, that's going to be 26 possible uppercase letters. And the digit is going to be the numbers 0 through 9. So it's going to be 10 choices for digits. So a total of 36 choices at each step. So you've got 36 choices here times 36 choices for the next number times 36 choices for the third password position, 36 choices times 36 times 36, and it's going to be the same way for the 7 and the same way for the 8 character password. We have 36 choices for each character. So this is really just going to be 36 to the 6th plus 36 to the 7th power for the 7 character passwords, plus there's going to be 36 to the 8th power for the number of 8 character passwords we can make. But we have to realize that this includes the possibility of having passwords that don't have digits. And what we need to do is subtract the number of passwords that don't contain at least one digit in them. So if I come back up here, what I can do is count. I can count. Let's see if we can be clear. This is all possible passwords containing uppercase letters and digits as indicated. And the problem is some of these passwords could be passwords like A, B, I should be doing uppercase, I guess. Some of these passwords, this could be an A, B, C, D, E, F. There's a 6-character password chosen from my 36 choices. The issue is it doesn't contain a digit. And the passwords like these are included in this count. And what we need to do is subtract off the passwords that don't have at least one digit in them. So the way that we'll handle this is we'll say, how many passwords are there of 6, 7, or 8 characters in length that don't have any numbers at all? Well, those would be the ones that we would just make from the alphabet. And if we're doing alphabet-based passwords, there's only going to be 26 choices at each stage. 26 times 26 times 26. There's going to be 26 to the 6th power ways of making a 6-digit password that doesn't contain a digit. We want to subtract those off. So I have 36 to the 6th, and I want to do minus 26 to the 6th. So getting rid of the passwords that only have alphabet letters leaves me with the number of passwords that have alphanumeric entries but contain at least one digit. And then we do this with each of the 3 types of passwords, the 7-character and the 8-character password. We say, hey, this is going to be 36 to the 7th. 7-character passwords, but we need to subtract the passwords that only have alphabet letters in them. Plus, we have 36 to the 8th possible 8-digit passwords, and then we need to subtract the ones that only have alphabet letters in them. So this is going to be, if we crunch this out now with a calculator, this would be the number of passwords that meet the criteria, number of passwords that meet the criteria delineated in the problem. Tree diagrams. So another way of counting things are using tree diagrams. So and these are typically going to be things where you put together in stages. You start with a root and then you branch off from that root. So here's an example. I'll let you read the paragraph. I won't read it to you. I'm just going to go straight to the example. So we have a band playing a concert trip to 3 cities. So it goes to city A, from city A to city B, and then from city B to city C. And what we see is there are different travel options. So they can travel to city A by bus or plane. And then we can travel from city A to city B using a bus, plane, or train. And then we can travel from B to C using a plane, a ship, or a train. So what you do is you say, hey, the band starts at home and they head off to city A, and there's going to be 3 ways they can travel to get to A. Tree diagrams always get messy. They're not very efficient for large numbers of choices, but I'm going to say, hey, with this node right here, if I wind it up at this node, then I know I'm at city A, and there's 3 ways I could have gone to get there. Let's see, I can travel to city A using, oh no, I only have 2 choices, a bus or plane, so I need to modify this real quick. To get to city A, I have to take bus, so I'm taking the bus to get to city A, or my other choice was, what was my other choice? Plane. I can take the bus or the plane. So either of these 2 nodes represent my being in city A, having traveled by bus or plane. And then I can travel to city B using a bus, plane, or train. So here I get to city A using a bus, then I leave city A and I head to city B. So I head off to city B, and I either take the bus, the plane, or the train. So at this node, I am now at city B. But if I took the plane first, I would still have the same 3 options. I could travel by bus, I could travel by plane, or I could travel by train. So I had 3 choices for each of those options. And now I need to leave city B and head to city C, and I can travel by plane, ship, or train. So here I traveled by bus, and now I'm going to take off again, and I'm headed to city C. And I can get there by plane, I can get there by ship, or I can get there by train. And if I went bus to city A and then plane to city B, now when I leave city B and go to, this is the city C column, I can travel by plane, I can travel by ship, I can travel by train. You can see why these get messy if you have large numbers of choices. If I traveled to city A by bus and from A to B by train, I can now travel from B to C by plane, by ship, or by train. And I wind up at city C. Same 3 choices here. I travel by plane, I travel by ship, I travel by train. And this is going to get ugly. I can travel by plane, by ship, by train, by plane, ship, train, and from here I can get to city C by going plane, ship, or trains, trying to squeeze it in there, plane, ship, or train. And the idea is with the tree diagrams, when you get done, you just count the number of nodes that you have here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 nodes. So there are 18 ways to make the tour. And the nice thing about a tree diagram is you can do things like ask specific questions. How many ways are there to do it if you do two of the possibilities by bus? So then you just look wherever you have 2 buses. Here's 1 bus, 2 bus. So there's going to be, hey, 3 possible ways where you do bus, back-to-back buses. So it has its uses. Notice we could have gotten this by the product rule just as easily. We could have said, hey, I have a 3-step process. I'm traveling from A to A and then to B, and then I'm traveling from home to A, from A to B, from B to C. So I have a 3-step process. And then I could look at how many choices are there at each step in the process. And I could have said, hey, I have 2 choices here. I have 3 choices on how to get from A to B. And I have 3 choices on how to get from B to C. So we could have done 2 times 3 times 3 is 6 times 3 is 18 and gotten the same thing. One more tree example. So how many bit strings of length 4 can be created that do not have two consecutive ones? So remember, bit strings, or we want bit strings of length 4. And bit strings were just sequences of zeros and ones, right? So for example, 1011 is a bit string of length 4. So how many bit strings of length 4 can be created that do not have two consecutive ones? So I could start off by saying, hey, I'm going to make my bit string of length 4. I'm going to represent it with a tree diagram. So I'm going to branch out. So for my first choice, right here, I can choose, I have two choices. I can choose either a 1 or a 0 to put there. So there's my first entry. And then regardless my choice to create my second character here, I'm going to have two choices, either a 0 or a 1. So I can either put a 1 there or I can put a 0 there. Here I can put a 1 or a 0. And then I get to the third entry for my bit string of length 4. I'm going to have two choices. Again, I choose either a 0 or I choose a 1. I choose a 0 or 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 a 1. And then I get my fourth choice. I have two choices. I choose either a 0 or I choose a 1. I choose a 0 or a 1. Here I choose a 0 or a 1. From here I choose a 0 or a 1. 0, 1, 0, 1, 0, 1, 0, 1. And now what we want to do is notice that we put the criteria on this that we do not have two consecutive ones. So we can't pick anything that has two consecutive ones. So let's see, this root here, 1, I can't go here, it would give me two consecutive ones. So I go 1, 0, 0, 0 doesn't have two consecutive ones. 1, 0, 0, 1 doesn't have two consecutive ones. 1, 0, 1, 0 doesn't have two consecutive ones. I can't choose this branch because I would get two consecutive ones. So here I go 0, 1, 0, 0 doesn't have two consecutive ones. 0, 1, 0, 1 doesn't have. 0, 1, 1, I can't choose that branch because I would have two consecutive ones, but I can choose this branch. I can choose 0, 0, 0, 0. 1 doesn't have two consecutive ones. 0, 1, 0 I can choose, but I can't choose this branch. And then what you do is you just count how many branches got highlighted. See if I can get my pin back here. So there's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ways to accomplish the task. So here the tree diagram was useful. All right, last example has an inclusion exclusion built into it, and we did inclusion exclusion. We did the inclusion exclusion principle when we were doing set theory. And what we did when we were working in set theory is we said, hey, if you have a set A and a set B, we said if we want to know the size of the union, so remember the absolute value symbol meant how many elements are in the union. We identified that we could just count the number of elements in A plus the number of elements in B, and then we recognized that the intersection, if we count the number of elements in A followed by the number of elements in B, that the intersection gets double counted. So we needed to subtract off the number of elements in the intersection of the two sets to get rid of the double count. And this was the inclusion-exclusion principle. So here we have how many bit strings of length 8 start with either a 1 or end with 2 zeros. So this one we've got to kind of tie all our rules in together. We can say, hey, I've got bit strings of length 8. 1, 2, 3, 4, 5, 6, 7, 8. And we can say I want bit strings of length 8 that start with a 1. So I have to put a 1 here. And then let's say I can put whatever I want everywhere else. Plus, there's going to be some number of bit strings, 2, 3, 4, 5, 6, 7, 8, of length 8 that end with 2 zeros. And I need to count how many of each type there are, how many bit strings of length 8 start with a 1 or end with 2 zeros. So I say, well, if I'm going to start it with a 1, there's only one choice there, times, and then it's bit strings, so these are sequences of zeros and ones. I'm going to have 2 choices everywhere else. And for my bit string of length 8 that ends in 2 zeros, I'm going to have 2 choices times 2 choices times 2 choices times 2 choices. So what I can see is there's going to be 2 to the 7th plus 2 to the 6th ways of making bit strings that either start with a 1 or that end with 2 zeros. The issue is that in this count, we've included bit strings that start with a 1 and end in 2 zeros. So there's a double count that's happened. 1, 2, 3, 4, 5, 6, 7, 8. We've double counted bit strings that ended in 2 zeros that also started with a 1. There's a double count. And the principle of inclusion-exclusion says we have to subtract the double count, or the intersection between the two types of objects. So we're going to go minus. So if we start with a 1 and end with 2 zeros, there's only one choice here, and there's one choice times one choice, and then we get times 2 choices for every other entry. And so this is going to be 2 to the 1, 2, 3, 4, 5, 2 to the 5th power because we lost 3 choices there. So we subtract the double count, principle of inclusion-exclusion. And that's a wrap.